Lightweight, portable, innovative. TESCO's 6330 meter site analyzer is the most versatile and complete tool for testing the entire functionality of transformer-rated metering installations. Contact us today for a free demo. Howdy, welcome to TESCO Tuesdays. We are back again for another week, and we're starting a little bit early here because we actually have something from last week that we had a question on. I just want to make sure we got Jim McGill online. Are you here, Jim?
I are here.
All righty. So we had a question on the meter forms, and you did some investigation on that. Would you like to address that?
Yeah, sure. The question was from one of our Caribbean customers, I believe, wanting to downsize his stock by being able to use a 9S meter to replace 6S and 8S meters. They're all transformer rated. It's a good question because if you look at the coil success meter is for a 3-phase 4-wire Y. It's a 2.5 element meter, which means it has 3 current coils and 2 voltage coils. So 3 plus 2 is 5 divided by the types of coils, which is 2, is a 2.5 element meter. The 8S meter is the same, but it's configured for a delta configuration. The A voltage references C, the B references A, and the A references C again. So again, 2.5 element meter. Now the 9S meter that he wants to use in the place of both of these other ones is a true, excuse me, 3 element meter that has 3 current coils and 3 voltage coils. So all 3 of the voltages are referenced back to phase installation and a 3 element installation so that you measure voltages AN, BN, and CN. Now in a delta, there is no neutral for starters, or almost never, and there probably was never one even brought in from the street from the voltage transformers. So a neutral would have to be running all the way from the supply transformers to the switchgear and then onto the meter cabinet so that you would have a reference neutral. And in tandem with that, with the 2.5 element meter installations, which the 6S and 8S were, there was probably never a B voltage transformer installed because it doesn't, you know, A and C. So neither of those meters are Blondel compliant really, because if the installation doesn't have a VT for the B voltage, there could be all kinds of DC driven motors or electronics and harmonics on that B voltage. So if it was badly unbalanced, the meter really wouldn't see what the shenanigans were that were going on in the B. So the punchline is, would the 9S work for the other 2? Yeah, it would if the customer was to add a 3rd VT for the B voltage and a true system neutral to reference all 3 voltages back to. I hope you're all still with me, but what that would mean is that there's an awful lot of work to do at those 2 sites, the 6S and 8S site, to bring them up to 3 element compliance. So unless he has a fairly good, formidable capital budget to make these system upgrades to use the 9S in all 3 instances, I don't know. I mean, it's a utility call, but to me, I'm thinking, no, you know, unless it's in their purview to change everything to 3 element metering, which it is in Canada. In Canada here, when you modify any 2.5 or 2 element metering installation, then Measurement Canada has said you must bring it up to true 3 element compliancy. So that's the answer that's the best answer I have anyway up here in Canada for that question for our customer is yes, it can be done, but there's a lot of work to do in the meantime. I hope that helps.
All right. Thank you so much for that, Jim. So yeah, if you guys ever have questions, things like that, we can always go back to our team. We kind of research it a bit and we'll always, let you know the answer to that, like we did for last week there. So moving forward to this week, as always, we ask you guys to mute yourselves so that we can hear everybody on the call, and it's just much easier for the participants as well. We do have the ability to mute everybody, so we'll try to do that if somebody accidentally unmutes themselves. If you're asking a question, you want to unmute, that's fine, but don't forget to put yourself back on mute. And then we will do Q&As at the end. If you have a question, just shoot it right there in the chat box. We'll try to get to that as we're going along. And we will have the presentations available afterward for you guys on our website, tescometering.com/tesco-tuesday. And we will also send out an email. Hopefully you guys are all getting those, and it'll have the presentation and the video link as well, so you can follow along with us. So I will throw it over now to John Williams, who is our engineering manager and will be presenting for today. And I'll let you go ahead, John. So go ahead.
All right, thanks, Sandy. Can everybody hear me?
Yep, we can hear you great.
Okay, good. Checking out a new camera today, so hopefully everything works out for us. Today we're going to talk about different meter forms, their applications, and a little bit about how folks like ourselves do the testing on those meters inside our test boards, and the differences between real-life applications for the meters by form and then how we simulate all the energy that we put onto the meter in our test boards. So, pardon me. So as far as an introduction is concerned, we'll discuss a little bit about background on meter testing and how we create phantom loads. We generate the voltage and current in our test equipment. And again, the discussion here will be generic in terms of how the voltage and the current is generated. Here also we'll talk about the self-contained versus transformer-rated meter forms and the differences there in both application and testing. And then as far as the testing of the meters go, clear up a little bit about single phase versus series parallel versus true three-phase testing of meters, and then a little bit about the applications of the testers for the different meter forms themselves. But first, oh gosh, did I have the right one up? Nope, I got the wrong one up. So my first mistake today. Pardon me, I brought the wrong one up. That's the right one. Oh, yeah, that's it. Sorry about that, folks. All right. And then, so first, we'll learn about a little bit about the polyphase metering, and as Jim mentioned earlier, a little bit about Blondel's theorem and how that applies to testing. And hopefully Tom's ready. And Tom, if you could take over this section for me, I'd appreciate it.
Sure, no problem. So if you notice, Mr. Blondel here is pretty young. Back in those days, they were basically inventing the electrical distribution industry. So he realizes in 1893, just as metering is becoming a thing, because now we've got commercial installations. We just had the World's Fair in Chicago. Tesla and Westinghouse have been granted the contract to build generators at Niagara Falls. So electricity is a big thing. Westinghouse has come out with some new meters that are better and more accurate than pretty much everybody else. And they're going to sell 100,000 of them in the 1890s, which basically is just about all the meters there were. Well, Mr. Blondel realizes that if you've got 3 wires, you've got to basically have 2 watt meter measurements. Okay, there's a little more to it, but effectively you need 2 watt meters to accurately measure a 3-wire system. John, you want to skip on?
Sure.
So if you have 4 wires, you need 3 watt meters. Okay, that seems pretty basic. So what are some of the, what are some of the problems with this? Well, we've got a lot of meter forms, which is what we're talking about today. We talked a little bit about last week. Our basic 2S meter, the meter that we have over 85% of just about all of your distribution systems are probably 2S meters. They're not really the right meter to have out there. They are that's a 3-wire service, and you have 1 watt meter. Okay, which means the 2S meter does not meet Blondel's theorem. Well, what the heck does that mean? That means that it is not measuring your service very accurately. Okay, let's take a 5S meter. A 5S meter, we learned last week, you could wire it up in a 3-wire system, or you can wire it up in a 4-wire system. Depending on how you wire it up, that 5S service may meet Blondel's theorem, or it may not. Okay, John, you want to go on?
Mm-hmm.
All right, so here's Blondel's theorem in practice. This is a 5S meter. All right, we got a 3-phase, 3-wire delta with 2 CTs. You click on that, John, you'll get a little bit. There you go. There you go. Now the 2 voltage measurements, one side common to line 2, current measurements on lines 1 and 3. This satisfies Blondel's theorem. So in this case, we've used a 5S meter in a 5S service, and we did it correctly. So everything is good here. Go ahead. Now we've got a 3-phase, 4-wire Y system with 2 equal ratio CTs. So very similar. We're using the same meter. We're using that same 5S. But now we are not meeting Blondel's theorem. We are not accurately metering this service. All right. John, flip ahead again. All right. So in that previous example, and this is more just for fun, don't worry about it. What are the assumptions and what are the errors? Well, the right answer mathematically, we put down. What did we actually measure? I wrote that down mathematically. Continue on there, John. And after doing lots and lots of math, keep going. Keep going. All right. So we get an error, and we can calculate what that error is even. All right. So the calculation is there on line 3, but what does that really mean? What that really means is, let's say we had VA was 117 volts, VB was 120, VC was 119. Okay. That seems like something that you might see out there. That's pretty good, actually, right? You got a power factor of 1. That's extremely good. So everything looks good. My meter is perfect. Everything's right. And yet I am getting an error of almost 2%. All right. So we've got a bit of an issue here. Keep going, John. This is out of the power measurement handbook that Dr. Hardy put together. And what it demonstrates to you is that if you've got a perfectly balanced load, okay, with a power factor of 1, your 2S meter, that 5S meter that we had, are actually going to be perfect. You're going to be able to use a non-Blondel solution, and you're going to get the right results. But as soon as you start unbalancing your load, as soon as you start moving away from a power factor of 1, you will start to create errors. Even though all the equipment is working correctly, you've wired up a bad solution. How bad does that solution get? If you look over in the far right column, you can see that it starts getting over 2%, 3%, 4% as it starts getting really bad. All right, now, if you had a Blondel solution, would it be better? It would be a lot better. So, one of the problems that we've got out there is our 2S meters. Why were they good for so long? Well, 2S meters, the Form 2 meter comes out basically in the 1890s is really when the predecessor of it comes out. And we stick with it for now 100 and almost 30 years. And the reason we did back in the day was the equipment was very expensive. Putting 2 watt meters out on every service was very expensive. So they didn't. But back in those days, the power factor was pretty much 1. The voltage was relatively good on all 3 phases. When I was growing up, because I'm really old, What did we have in the house for a load? We had an old refrigerator. Well, that was an inductive load. We had a bunch of incandescent lights. We had a power factor, and probably all of our neighbors had power factors that sat right about 1. As long as the power company gave us relatively balanced voltages, and we had our house was wired correctly, so we had a relatively balanced load, that meter gave pretty close to 100% every single time, every single month. Fast forward to 2021, what do we have? A lot of folks working from home. Our kids are going to school from home. We've got switching power supplies. We've got all kinds of things. We've got TVs that have switching power supplies now. We've got a lot of non-inductive loads, a lot of loads that are moving our residential services further and further away from a power factor of 1. As that continues to occur, our 2S metering is going to go further and further south. It is going to get worse and worse and worse. Even though the equipment is working perfectly, our metering, we're going to be losing revenue as utilities, going to be losing revenue from our 2S metering. So the 2S meter is not a good solution, and it all goes back to Mr. Blondel. Basic theorem, count the number of wires, that's how many watt meters you should have. If you've got those two things, you can wire it correctly. If you don't, you won't. So, John, back to you.
Right. Hey, thanks, Tom. Always interesting learning about Mr. Blondel and all the problems that can arise from the types of meters that we have out there.
He would have done us all a big favor if he'd have just stayed in bed that day. Have these problems to deal with now.
That's right. That's right. So a little bit about testing meters now. So Tom spoke about, and we'll touch on it a little bit, about the real life applications, trying to conform to Blondel's theorem in terms of metering accuracy and difference in loading. When folks like TESCO create meter test boards, we do that and we create the energy that we put out to both the reference standard and to the meter in what we call phantom power. I'm sure most of you have heard the term phantom power before. But what it is exactly is we're trying to create a situation whereby the meter is measuring energy as it would in the field, but in a lab situation. And why do we do that? So in order to test a revenue grade meter, for example, to the ANSI C12 specifications, we have to test that test volts and test amps. Simple example would be a 1S meter. You have 120 volts, you have a TA of 10 amps, let's say. Without employing phantom loading, the test board would have to consume 1200 watts just to test that 1 meter. But if you created the energy for the meter using phantom power, the test board would only consume 150 watts. Now, you have for the bigger utilities, you have whole walls full of test boards, or even, a simple 4 or 6 position board, that adds up to a lot of energy, right? A lot of heat. Folks in the lab are going to get upset because now the temperature in the room just shot up because of all the energy that's being put out into the atmosphere. So phantom power is very simple in its concept, a little bit harder in practically producing it, but we've of course perfected that. It separates the voltage and current into 2 different sources, if you could think about it, 2 different power supplies, if you will. One is a high voltage source, and it's at very low current. So again, the power output on that channel is very low. And then high current at very low voltage. Again, a low power situation, but you combine the high voltage and the high current and apply that to the meter. From the meter's point of view, it's a real loading condition. And that's really what we want to test for. So how do we do that? So any modern meter test board will create the phantom power, both the potential and the current, using a couple of simple steps. Again, simple in concept, a little bit more difficult in execution, but basically it starts with a processor of some sort that produces a sine wave. With the types of processors that we have nowadays and the accuracies and speeds, we can create really, really accurate sine waves using digital electronics. Once that sine wave is produced, that's kind of the basis where you're going to generate your power from. That's pushed out to an amplifier board, which does exactly what it says. It increases the amplitude of the signal that's riding on that sine wave. And then finally, there's a transformer stage where, in this case, for those of us that are building test equipment, where all of our transformers internally are stepping up the voltage and stepping up the current. So we have CTs in our equipment, we have PTs in our equipment, but they are designed and specially wound so as to step the amplitude of the two signals up. And of course, for single phase units, you have one of these circuits each for voltage and current, and likewise for the series parallel type of arrangement. The only difference there for the series parallel arrangement is on the current side, you're actually driving from the amplifier section into the primaries of up to 3 CTs, right? So you still need that separation from the current side to get to the meter and meter it accurately. Here, though, in both single phase and polyphase series parallel type of arrangements, you can accurately test the meter to a degree where the voltage and current are always going to be in phase with one another, and likewise from the A phase connection on the meter, B phase, and C phase. So everybody's all going up and down at the same time. And from the metering standpoint, if we look back at what Tom spoke about earlier in terms of Blondel's theorem, he spoke about it in terms of 3-watt meters. So even your polyphase meter forms are really 3 meters in some cases, at least the Blondel types are separate watt meters inside the meter. So being able to do this single phase is possible because of that independence within the meter. Now, of course, we all know there are some differences in the applications and for polyphase meters. So really what you want to do is test those meters in a true 3-phase environment. In that case, you don't use the series parallel connection, but you actually have independent channels, 3 for voltage, 3 for current. Everything works independently of one another. So here's some examples, and I'm going to go through a bunch of these examples. It's going to take a while, and we have some of our folks that have some outside metering experience are going to give some examples of where some of these meter forms are used. But in general, I'll talk through the schematics of the different meter forms and how they're applied in the field, and then how do we simulate that energy into that meter for meter testing using the phantom loading that we just spoke about. So the simplest form that we have here is the 1S meter form. It's typically a single phase 120 volt application where you have one side of a standard 3-wire pole transformer going into the meter. You have the voltage coil across and the current coil down. The meter is in line with the power source and the load, and is measuring the energy directly into the customer load. Right. This is a self-contained application where there's no other external devices needed for the meter to meter properly. So what does that look like? Does somebody needed to speak?
Yeah, I was just going to chime in, John. It's Jim.
Yeah, go ahead.
So where would you use these? If you put a little shed out behind your house, a garage or something like that, you only needed 120 volt power for just maybe some lighting circuits and a bar fridge, of course. Then you might want to use one of these installations. Where they're really popular these days is in metering camping trailer sites. Okay, so when the trailer park owner wants to make sure that everybody's paying their own share of the bill, they would install one of these systems on a post outside of each of the camping sites. Okay, so they only use 120 volts and not too much of it, so that's a big use for a 1S installation these days.
Right, and actually, I did a TESCO Tuesday presentation a few weeks back, and it was on smart metering, which is these smaller format meters that are going on to LED streetlight poles and measuring some other interesting applications where you need a small format meter. And their meter form is basically a 1S, right? They've got a single coil for the voltage and a single coil for the current. And there's some other electronics that go into those devices that are used to control the output, right? So they're dimming lights and turning them on and off and things like that. But in essence, the metrology for those devices follow a 1S meter form. Now there's talk about perhaps boosting that a little bit. The smart meters it can actually take 240 volts across the volt coil. There's been talk also about some 480 units, but in essence, they're just a simple single voltage, single current element. So we see here in this diagram the application of what I was talking about before in terms of the phantom power application. So in reality, when we talked about the real installation, you had the power going straight through the meter and consumed by the load on the downside of the meter. Here, to create the phantom load, we have that last stage of that circuit that we talked about, which is a potential transformer. So we have that isolation here. And again, I didn't draw all the other electronics that go around the test board, but certainly for a 1S meter, you would tie your leg 3 to ground and just apply 120 volts to pin 1. The current transformer coming out of the amplifier circuit would then be wired independently from pins 1 and 3 on a 4-jaw meter, and that current would flow out of the top of the CT down through the current element and then back on the return. And because these transformers are independent from one another and not tied to anything else, they can float at whatever voltage the potential transformer puts out. So that's how we can create that phantom power. So the meter is just looking at what the voltage is across the voltage coil, what the current is across the current coil, multiplying the two of them together and measuring the phase angle between and putting out a watt-hour reading. So we're just doing the exact same thing here, but consuming much less energy in the application to the meter. The next one we have, of course, is I don't think we need a whole lot of examples here, but this is our standard 2S meter, where this is our typical residential meter. We have a 3-wire pole transformer, 3-wire source into the house, non-Blondel compliant, and you have your voltage across, your current through the 2 legs going into the circuit breaker panels in the homes, and pretty simple application. We all know mostly about this one. One thing to keep in mind here as I talk about the test application for each of these meter forms and how that applies to what Tom spoke about earlier in terms of Blondel and things like that. The test board is built to create, when you're testing pure accuracy per ANSI C12, it's generating the potential and the current in a very highly regulated way so that all the loads are always balanced perfectly when you selected to do so, right? All the ANSI specifications say that those there's the specifications on how far that can deviate per channel, but basically we're creating the absolute perfect conditions so as to zero out any Blondel type error. Now that being said, the newer test boards, like I talked about before, with all these digital sources and processors and software and all that fun stuff, they can put out, you can set them up to act differently, right? You can test the meter with an imbalanced load. You can test the, offset voltages, you can test offset currents, and still do a simple accuracy test, right? Based on those conditions. If any of you are interested in real life testing of Blondel's theorem, you can do that with the TESCO test board, for instance. Here we see the 2S application. I drew the potential transformer across the voltage coil here. And that is the case for a lot of test boards. We also do, when we apply voltage here, we actually do 2 potential transformers, one off of pin 1, one off of pin 3. And so we simulate that 120 volt, 180 degrees opposed on the voltage. And similarly, we match that with the currents. Remember too, as we go through these testing scenarios, when we apply when I talk about all these different meter forms, remember that a test board has to do all of these meter forms, right? So there's a lot of switching and circuitry behind the scenes that apply the potentials and the currents to the right places on the meter form. So that's what I was mentioning earlier about, it's kind of simple in function, but the application in terms of the metering test board is a little more complex in order to get all of these to work on one socket. All right, so another application, we go to our first transformer rated meter form. This is the simplest of the transformer rated meter forms, the 3 and the 4S. So here again, we have our 3-pole or our 3-wire pole transformer. In this case, we're taking the voltage directly into the voltage coil. And then on this diagram, at least, we have our CT for the current application to the current coil in the meter. Here also, this is a 240 volt application for a 3S. We've gone back and forth actually on our test board setups as far as default conditions for 3S meters. It seems like most folks are split 50-50 in terms of whether it's a PT application or not PT application with just the CT on the current lines. But this diagram here shows the voltage coming directly in and the current coming through the CT. I think, Kevin, did you have an example on this one?
This one, John.
Oh, not on the, oh, you have the next one, right?
John, a very big use for this type of installation would be a farm, where you've got a line coming in and out to the farm and a CT up on the pole, and then it's called a CMS, a central metering system. And then above the metering, you would branch off to your barn and your house and your drive shed and a bunch of other things. So these things are real big out in the rural applications. Another little thing about this installation is you'll notice that there has to be a 0.5 multiplier associated with the billing on this account. It's because, as you can see, from the X1 on the transformer, the current travels through the CT left to right, and then on the return leg, which goes back to the X2, it comes back in, it does a 180 and goes back through the CT in the same direction, and then returns to the transformer. So what's going on here is the CT is seeing the total load of this service twice. So in order for you not to double bill the customer, you have to have a 0.5 billing multiplier on this installation.
Very good point, Jim. Thanks. So here again, because of the ability for a test board to vary both the voltage and the current according to whatever you want to see the meter read, you don't have to worry about those factors like Jim mentioned, other than that becomes part of the standard setup and what the computer produces to put out to the voltage and current transformers out to the meter socket. So one thing to keep in mind when you're applying a 3S meter on a meter test board, again, we typically have been defaulting the service to 120 volt, which would be a potential transformer application for the 3S. Reason we do that is typically these are single voltage meters. And if we default it to 240 and you have a 120 volt meter in there, bad things are going to happen to the meter. But of course, you could always change those defaults if you're only using the 240 volt 3S meter. The next one we have up is a step up in complexity again. We have now our 4S transformer rated meter, similar type application, 3-wire service. We take the 240 volts across the potential coil, but this time instead of doing that double wrap and the 0.5 factor on the meter on the that we see on the 3S, the 4S has those two current coils and can accept the outputs from the two CTs. And I think this is the one you wanted to talk about, Kevin, right?
Yeah, so down here in Texas, they use a lot of the 4S meters on like smaller restaurants that may have for air conditioning load. It's only for single phase instead of 3-phase. And then we also have a lot of large ranch houses that are more than the 325 or 320 amp meter that actually higher than 400 amp on these large ranches. So they always go to the 4S meter on these.
Okay. Thanks, Kevin. So again, you see the similarities between the 4S transformer rated meter form here and the 2S self-contained. This again for higher power situations like Kevin mentioned. Again, here we do the same thing in testing the meter. We put the potential transformer across the voltage coil and use two current sources to put the current to the meter. Again, a lot of these are going to be repetitive as far as the application, and just know that the different situations for current directions and so forth, you'll get to like Z coils later. Those are all simulated using the software. The next one is the Jack of all trades 5S meter. Tom referred to that earlier in the Blondel discussion. This is where, this is kind of like I said, the Jack of all trades. I picked a 3-phase delta application here for the real installation type. Here you see we have the 3 phases wired to the two potential coils, and then the 2 CTs going out to the 2 current elements on the 5S. Of course, as most of us know, the 5S is probably the one that can be used in the most different situations. You can use this on a straight up single phase. The thing about the 5S in terms of meter testing, and folks here know that this is the one that I complain about most, because the 5S is different than all the rest of the meters in that it has a potential coil where every other polyphase meter would have a current element. And that might not seem to be a big deal, but in the days before we did a lot of electronic switching and we had computers and so forth in our test boards, it became a relay connection nightmare for us, because typically For every other meter form, we can connect our current transformers right to the A phase, the B phase, and the C phase current elements where they would normally lie on every other meter. And if somebody said they wanted their board to work with 5S meters, that became a bit of a trouble for us, where we would have to make sure that we didn't apply a CT across where a voltage coil would be. Obviously, you end up with a short circuit and then blown fuses or circuit breakers, and it tended to make a mess of the test board circuitry. Like I said, nowadays we've got computers and software, and we handle that a lot easier. But in the old days when we were doing this with relay connections and so forth, it became a bit of a challenge, as we say. Anybody have any information on the 5S applications? Any once, any twice? Okay. So here we see now we do a dual transformer arrangement here for the potential. So we have the two voltage coils. We apply the voltage independently to each. And because, again, we have that computer-driven output, we can make those two potential coils look like a delta service, right? In this case, kind of an open delta service. And then the two current transformers on the current elements. Again, here we can, with this arrangement, we can simulate a typical 3-wire 240 service, all the way up to a 240 or a 480 delta. And just with this arrangement and some software. Those 6S is again a transformer rated installation. This time we have 3 current coils and 2 potentials. Similar here, we have the 3 pole transformers, the 3 current transformers driving each of the coils independently. In the case of the B phase, we have that crossover Z coil arrangement. This is a little bit of mathematics involved in getting that to work in terms of the current application from the computers. But here, again, we have Jim on a 6S applications.
Well, this is the one that we started off the presentation by talking a bit about. It's
Exactly.
2.5 element meter. Blondel says that you can measure n conductors with n minus 1 elements, but this has n minus 0.5 elements, which kind of knocks it out of Blondel's equation. So, these things were in great use for a long, long time, but because of the B, we really need a good voltage reading on the B these days. So they're converting any of this 2.5 element stuff over to 3 as quick as they can up here anyway.
Good. Thanks for that. And again, in this case, we have the 2 potential transformers. Typically, again, as you can see, it's getting a bit repetitive in terms of the test board applications here. But realistically, it boils down to the number of elements in the meter dictates the number of phantom transformers needed to drive that meter. And then any of the phasor relationships between the voltages and the currents and between phases themselves can be handled with software. In the 8S situation, we have a transformer rated meter here again. In this case, we show the 3 CTs, and this is a 4-wire delta. So we have a high leg. This diagram is called the wild leg. So we have a 208 from the wild leg down to neutral. Then we have 240 line to line and 120 line to neutral from the other 2 phases. This application has so this is the transformer rated application. The self-contained mirror of this, I guess, is the 15S, and we'll talk about that in a minute. But again, as you can see, as we go through these, we're getting more and more complex in the number of elements and the number of connections and so forth, and the applications in the field. Typically, as far as I know, the 90+% of the application for the 8S meter is for the higher current applications for a 4-wire delta. Okay. And again, here, for the testing purposes, the voltage transformer is going to go across basically the 240 coil here. And then we have a second one that'll go across the 120 coil here, the neutral. And then the 3 current transformers going into the current elements. And of course, probably the most popular of the transformer rated forms, the 9S, typically applied to 4-wire Y circuits. In this case, we have direct voltage input and 3 current transformers. The one thing that I know about the applications here is, I guess, I was at a meter school once, and they talked about the fact that maybe 9S meters, when you're putting in new installations, you might want to take a look at that, because as far as the installation costs are concerned, for it versus a say a 320 class 16S self-contained meter might make more sense depending on the actual application and the currents that are going to be pulled into that load, right? So if you have a 320 class 16S meters, then you don't have to worry about your CT cabinets and all that extra wiring and test switches and so forth. But you can get the same accuracy out of a 16S so long as the load stays within the 320 specification for the meter.
John, this is Kevin in Texas.
Yes, sir.
So everybody down here is going to the 9S meter because they can get different voltages from the Y bank for 12208, 12240, 277, 480. They can get whatever they want. It's much safer, cleaner, easier to work with, especially if you're troubleshooting. So everybody's going to the 9S meter down here and getting rid of everything else.
Oh, wow. Okay. And is that just for testing at the service location and the wiring and so forth with test switches?
Yeah, so it's easier to be able to test. Everything's more accurate. And again, the higher load with all the industrial load that we have down here in Texas with everybody moving here.
Mm-hmm. Everybody wants to be down there with you in Texas, eh?
What about, Kevin, you were talking about some of your 4S applications earlier and where they're still using those.
Yeah, so yeah, we talked about with the 4S, again, with the smaller restaurants that don't need 3-phase air conditioning loads, there's, using air conditioning on a single phase. The other one is large ranch houses that we talked about. So down here, we use a lot of 4S and 9S meters.
Okay, good. And again, simple application from the test board side of things. We just have the 3 potential transformers, 3 current transformers into the meter socket. All right, so the next one up is self-contained 12S meter. This one is typically applied in the network configuration, where you have basically the top of a 4-wire Y directly in through the meter into the customer load. Again, you have 208 phase to phase, 120 from line to neutral. And then the test board arrangement, similar application as before, 2 PTs two CTs into the meter. This is one of the simpler ones to apply in the test board. Other than the thing that you have to make sure of in the application in the wiring is the 12S has the neutral connection either at the 6 o'clock or 9 o'clock position.
A lot of irrigation wells in Texas are using the 12S meter.
Yeah, also very popular in high-rise condominiums where you have a three-phase four-wire supply to the building, but each condominium or apartment, if you want to call it that, is a 208 supply. So the meters are arranged so that apartment 1 gets its energy from phase A and phase B, apartment 2 gets B and C, apartment 3 gets A and C, and so on up the building. And they do it that way so that it eventually balances out the three-phase load. So they're drawing from different phases of the four-wire arrangement, three-phase four-wire.
Yeah, here too in the States, I think the most common application I heard of is just like Jim said in big apartment buildings, condominiums, etc., where the balancing of the three-phase load is easily done applying the 12S meter in the arrangement that Jim mentioned. So now we're starting to get into the bigger polyphase forms. This here's the 14S. Again, we're similar to the 6 transformer rated. This is its pair in the self-contained. We have that cross-phase element in the middle for the current and the three-phase line coming in. On the meter test board side of things, again, we have the two potential transformers into the two potential elements, the 3 current transformers into those elements. And again, as I mentioned before, all of these different meter forms and the different connection points here, it's all done electronically behind the scenes. So even though these diagrams are simple, you should see the one that we have to put together that connects all the different meter forms into one socket. Lots of lines and confusing information. On the next one is, I mentioned before, this is the 4-wire delta application with the self-contained. This is the 15S meter, same situation as its transformer rated counterpart, the 8S. So again, you have the 4-wire delta with the center tap ground on one of the legs. And you have the wiring, as you see here, directly in for the 3 lines, one side being the wild leg, and that is the one that's attached to the ground point. And the other 2 legs are tied across the single voltage element here. And we see the similar arrangement here that we saw in the 8S as far as the test board is concerned, with the 2 potential transformers, 3 current transformers, and like I said, similar to the 8S installation. Finally, the 16S, as we mentioned before, this is the counterpart to the 9S in terms of self-contained applications. Kevin made a good point in terms of the installations in his territory, going more to the CT rated ones because of the ease of testing and safety concerns. But again, this is something that you may want to look at in terms of the cost of installation as well, where if you get your load is capable of being measured by the 320 class 16S, that might make sense for you, so as to cut down on all the installation and the additional wiring and so forth. Okay, and then again the meter test board application here, very similar to the 9S with the 3 potential transformers and 3 current transformers. I did realize one thing that I forgot to mention earlier. One of the things with regard to phantom loading and test boards and so forth is so on the residential applications with service disconnects built into the meters, right? So your 1S, your 2S, and your 12S meters. A lot of the meter manufacturers put in kind of the high-powered relays in there to do the disconnect switching, which require a lot of current, a lot of VA to open those disconnects and close them. So, as I mentioned before, in terms of generation of the voltage and the current in the test boards, those 2 channels, the voltage and the current, are typically low power outputs, even though they're high voltage, low current, and high current, low voltage. So one might run into a problem with activating these disconnects if they're consuming 750 up to almost 1,000 VA in rush to pull in some of these disconnects. On the TESCO boards, we do things a little bit differently there. When we do a disconnect test, we actually go off a standard line transformer that has up to a 1,000 VA capability to drive those disconnects. So the digital sources used to drive the potential transformers there are usually rated around 90, 100 VA, something like that. So a lot of them are not capable of pushing through those disconnect relays. So that's why you'll find on the TESCO boards, we'll go into a disconnect mode where we switch off to a higher power application, because in those modes, you're not really going to be doing the meter testing, but you're just trying to cycle that disconnect switch for functional testing. So we switch over to that transformer in order to power up those relays. So that's something that you might want to look out for when you're running tests. The other thing that we can do when we're doing disconnect testing is you can still use the digital phantom current running through the meter while you're doing the disconnect test, so long as the current is synced in phase to the line current coming in off of the transformer, right? So when we set up our disconnect testings, we read off the phase with our metrology off the phase from the line power coming into the unit, and then we sync our current output to match it in phase, so that you can actually open and close that disconnect under real load. And we're almost out of time. I think we have about 5 minutes left. If there's any questions out there, we've got a slew of TESCO people here willing to answer those questions for you.
And one other thing, John, about the 16S, Kevin was mentioning earlier to me that now that they have the 16S in a 320 amp version, so it's also an alternative for a light industrial or a light commercial application. I did not realize that they had a 320 version of that meter as well. So a good choice. And then if it's a little bit more, maybe the 4S. If you've just got this, if you've got a heavy load and just a single phase, as Kevin talked about, and then of course the 9S is really ideal for most of those things.
Another interesting thing about the 16S is it's available for most meter manufacturers in an auto ranging voltage. So you can not only, up here we use 347, 600, and 12208, and you can use the same meter in either application. Down there it's I guess 12208, 277, 480.
Right.
But they're universal. So there's only one meter manufacturer that doesn't make it that way, and I'm not going to mention them because they sell a lot of meters up here. But anyway,
yeah, we don't like talking about that. Thanks, Tim and Tom. Good points there. I have been seeing a lot of 320 class 16S meters being tested by a lot of our utility partners. And that seems to be becoming, of any of the 320 class meter forms available, I think the 16 has been the most popular over the last few years. And I think it's because of that application that I was talking about, whereby you might want to look at, as far as cost wise, in terms of the installation versus the 9S and all the sundry equipment that goes along with it.
All right, guys, looks like the chat's a little bit quiet, so I don't know if people are still typing or maybe there are no questions because you did such a great job. But we can hang on a few minutes for you guys. Anybody shy doesn't want to ask a question, you can always email it into us as well. In the chat there, I did put the website where we'll be posting the presentation as well, tescometering.com/tesco-Tuesdays. And we will be sending it out as soon as we have the video ready as well. So you can always go to our page as a resource to get that information. You can always email us. We'll hang on this chat for a little bit, see if you guys have any questions. And hopefully we'll see you guys next week for our test switches and hot sockets. So I'll leave the chat up for a little bit, and you guys can let us know if you have any questions. Otherwise, have a great week, and we hope to see you all next week. Thank you so much for joining us, and we'll see you next Tuesday.
Thanks, everybody.
Thank you.
Lots of thank yous, Andy, but no questions. So I guess I'll just toddle off and go to my next fire to put out.
Absolutely. Thank you so much, Jim.
Have a
Thanks
great day.
for the input, Jim. Appreciate it.
No problem. Take care now.
Bye now.
Hey, John Carroll, I just thought I'd quickly just chime in at the end here, not related to this, but kind of. I'm getting a lot of, I don't know, feedback from customers or utilities where they're considering putting the 16S in. There's budgetary reasons. There's also this OSHA regulation out here in California, which is really pressing them not to test CTs in the cabinets. Right. So have you heard anything to this effect?
In a different area, but yeah, the CTs, and that's another thing that rolls into that cost question, right? So I've had to deal with in other situations with customers talking about how the CTs and PTs are managed, right? So they're typically managed as assets. And under that asset control, they are, especially some of the bigger utilities, have a certain amount of, rules and regulations as to how they're tested, how accurate they are, their applications. Right. I mean, there's a lot of things that go into it, right? Because all the way down to the programming of the meter, right? So you have to have have to have the right CT and PT factors in the meter. We've had anecdotal references back to us when we released the 6330, the site analyzer, where they'd come up on an installation and some of the biggest money losses that the utility can have are on these big transformer rated installations where it could be anything from a wiring mistake all the way through having the wrong factor in the meter. Or
on reverse CTs, which they haven't discovered.
Right, and or cross-wired, upside down. You go, typical example I use for field installation issues is, you have a 3 CT installation, and all you have to do is wire one of the CTs backwards, and you get 1/3 of the billing. Yeah. Right? And or if you have the wrong factor in there, if you have two CTs in an installation at one ratio, and the third was put in because it had a problem and somebody replaced it with the wrong ratio, and now you're metering one of the three phases at one ratio and the other two at another ratio, and God knows
Right.
what the factor is in the meter to accomplish that. So there's a lot of things that go into transformer rated installations, as we all know, and you know, some of those headaches can be gotten rid of
Yeah.
by using the self-contained.
Yeah, that would be maybe that's a future presentation, Andy. Make a note of that one.
Yeah.
Sure
That's
thing.
probably going to happen more and more in the future, so we do a lot of research on it. But yeah, I've already heard a few folks mention it. I think the cost of replacing everything is outweighing the benefit at this point, but there's going to be a crossover.
So are you there, John?
Yeah, I'm here.
Yeah. Which one?
Well, yeah, which one? Sorry.
I don't know if you can hear me, but there's a question coming in for the 2S from Anika. So I don't know if she wants to unmute herself and or himself. I'm not sure, but wanted to know if there's any information out there to make a recommendation to move away from it, from the 2S, as we use it a lot for residential metering.
Tom actually brought that up earlier in terms of the non-Blondel situation and the inherent inaccuracies. If you have a 2S application where you have an unbalanced load, don't know how often that's going to happen but with the changing loads, as we know, and especially in residential applications. You know, you might get into a situation where you start moving off of your 1.0 power factor, or you start to get into to imbalanced loads or things like that, where the 2S is going to become a little more inaccurate, and you know, you could lose up to 1% or even more on some of those examples that Tom gave earlier. I guess, guys, chime in here if you will, but I would guess the next step would be to do a 12S application on the on a residential service to be both Blondel compliant and a bit more accurate without having to add a whole lot to the installation to switch those out. And I'm not sure what the cost differential is from a meter manufacturer between a 2S and a 12S meter form. I can't imagine it's a whole lot, but you get a Blondel solution. You still get the ability to have service disconnects, because 12S is a common form for service disconnects, as is the 2S. I just know that the meter manufacturers themselves are probably producing, just because of their requirements from the utilities, are probably producing a lot more 2S meters than they are 12S meters. But certainly it's something to look into if that's a concern.
Well, I'm still hanging around here like that smell, but the 2S meter may not be Blondel compliant per se, but it's still amazingly accurate because it's just a single winding. It's a simple single phase winding. It's not different phases. It's the same phase entering and returning from the service. So whatever's going on the supply side is going on the return side as well. Yep. They're balanced. They're always the same. KVA in must equal KVA out. So there's really not much reason to move away from it.
Oh, okay. All right. Thank you so much. That's what I was concerned about, because, like I say, we use that application a lot in the Bahamas, and we normally only use the Form 12 when we have like a 3-phase bank, and we're feeding the customers off of the 3-phase bank, and we need we use the 208 voltage in that case. So we use the Form 12 in that instance, but we normally use the 240 meter, which is the Form 2, in every other instance. And so I just wanted to make sure that we weren't losing. But you're saying that we're good in terms of our metering.
Yeah,
so that's what I was concerned about.
Yeah, I think as Jim mentioned there, in most cases that we may have overstated some of the issue there. in terms of the types of errors you're seeing. Again, I only made my statement as to the 12S if you already know that you're losing billing because of imbalanced loads or problems
Okay.
with voltages and sources. If you don't have that, certainly stick with the 2S if you already have it in there.
All right. Thank you so much. Great
Mm-hmm.
presentation. Appreciate it.
You're
Also
welcome. Thank you.
important to note that the 12S voltages are referenced to neutral.
Right.
2S
Right.
is line to line, showing
Yeah.
240 volts. So if you were to use a 12S, you have to make sure that you have a proper system neutral to tie both of those voltages to.
Right.
Because it
Yeah.
measures A to N and C to N, or A to N and B to N, or whatever way you've got it wired up.
Right.
Yeah.
Yeah,
Not
typically
that's
the
our
neutral.
concern.
Yeah, typically, I guess on a 3-wire installation like that, though, you're pulling your neutral through your meter box anyway, so
Yeah.
it might not be that big of a change. But again, you're going to have to change your sockets and your boxes and all that kind of stuff to get that fifth jaw on there, to
Right.
get
The
the
fifth
neutral
jaw. The
connected into the
customer
meter.
would they don't want to take that cost anyway to put the fifth jaw.
Yeah, exactly, exactly. Yeah, because that's a customer cost at that point.
Right. All right then. Thank you so much.
All right, thank you.
I got to head out. Thank you, guys. Great presentation, John.
All right, see ya. Thank you.
Good job,
Thanks,
John.
John.
All righty, are we done? You think?
I think so. I don't see anything else, so we
All
are
right.
good. Thank you so
Okay.
much, John. Great job.
Okay. All right. See you guys.
All right. Bye, everyone.